Alright, so now that we've talked quite a bit about motion, acceleration, velocity, forces, stuff like that, we're ready to address this topic of circular motion. So, why do things move in circles anyway? Like turning a corner in your car, or racing track NASCAR stuff. I'm not a big sports guy. I don't really watch racing or anything like that. But anyway, why do those cars go in a circle around the track? What's keeping them? What's making them go in a circular path? Possibly you've never thought about that before. But that's what the topic of this video is. So let's get started. Alright, circular motion. It's an interaction of force, velocity, and acceleration. Alright, so here's a couple examples. I don't know if you're familiar with this. It's an Olympic sport. It's also a sport they like to do, a slightly different version of it in Scotland, which I believe is where this guy here is possibly from Scotland. This dress skirt that he's wearing, it's actually called a kilt. So it's not womanly in Scotland. It's actually manly to wear a kilt. Anyway, he's throwing this thing, which is called a hammer. Alright, in the Olympics, I think it looks slightly different from that, but the Olympics has a hammer toss. So what's the basic idea? Well, the guy spins in a circle, gets up some speed, and then eventually he stops his spinning and lets go. Let's go, whoosh, the hammer goes flying. Alright, so why does it go flying when he lets go, but it goes in a circle when he's holding it? Interesting. Another one, right? I was mentioning cars, race cars. Why do the race cars go around the curve instead of simply sliding off the track and continuing their motion in this direction? Interesting. Well, that's the topic. So those are two examples of circular motion. Let's move on. Alright, you can see at the top there the question I was asking. And let's get into that. Alright, we're looking at the guy who's throwing the hammer. So he's doing the hammer toss. This is a schematic, obviously. Top view, so we're looking straight down at him as he spins this thing in a circle. What you have going on here is a velocity vector, which makes him want to go, makes the hammer want to go that way. And then you've got actually another vector involved here, and it's this one. What is that vector? Well, it's the vector that's caused by this guy holding on to the hammer. Alright, and that is a force vector. Whoops. So the force vector, and it turns out that force is actually really important. That force is the reason that the thing follows a circular path, rather than flying off straight along its velocity vector. Because you may remember from Newton's first law of motion that objects in motion tend to stay in motion unless they're acted on by a force. So the force sort of causes this interaction of vectors, and the resultant motion is a curved path like this. Or at this particular moment, the resultant motion would be something like that. Alright, that's the basic idea. Let's get into a little bit more specifics about that. Alright, first off, this force, it's called this force, it's toward the center of the circular path, so it is center-seeking. So what is the name of this center-seeking force? And the answer is centripetal force. So it's called centripetal force. Centripetal, basically toward the center. It's a force that seeks the center of the circle. So this force tries to pull the race car toward the center of the circular path. Now, of course, his velocity tries to send him flying straight out of the circle. So velocity wants to go in a straight line. The centripetal force wants him to go toward the middle, and they compromise, and he ends up following a circular path. All right? So just to get into the nitty-gritty just a little bit, we're going to talk about the details here. So no pictures on this slide, I'm afraid. But I'm going to summarize basically what's going on here. So the circular motion, as we mentioned, is caused by that force toward the center. If there's no force toward the center of the circle, then there is no circular motion. The object is just going to go in a straight line. All right. So if we talk about Newton's second law of motion, we know that that's this formula, F equals m times a. Force is equal to mass times acceleration. Now, there's an interesting implication in that formula, an interesting little fact, and that's this. If there is an acceleration, if you cause an acceleration, you must be causing a net force. There has to be a net force acting on that object. Otherwise, it can't accelerate. All right? So any object that is accelerating must have a net force. Remember, acceleration in the physics sense of the word. All right? In the physics sense of the word, which means any change in its velocity. Interesting, because a change in direction is a change in velocity, right? So changing direction means changing velocity, and that, my friends, is an acceleration, all right? So if you're having an acceleration, you need to have some net force acting on that object. Where does the net force come from? In the case of circular motion, the net force is the centripetal force. Dude, that's so cool. All right, so just to sum up, if we were to go back to our pictures of the guy with the hammer and the cars racing around the track, where do you think the force comes from? This centripetal force? Well, in the case of the man with the hammer toss, the force comes from his arms, from his friction of his hands holding on to the hammer. So the force comes from him holding the hammer and friction there between the hammer and his hands. In the case of the cars, the force comes from the tires and the surface of the track. So mostly it comes from, the force there comes from friction of the tires with the track. Sometimes if the track is banked, it's at a curve. If the track is kind of banked like this and the car is sitting there on the track coming around the corner, then you also get a little bit of a force outwards toward the center of the circle just from the surface of the track because it's at an angle. Don't worry too much about that. A lot of the force of the car coming curving around the curve, most of it comes from friction of the tires with the road, but you get a little bit also from the banked curve if you happen to have a banked curve. Anyway, so the point is you need a force toward the center of the circle, and the more force you can get toward the center of the circle, the better chance you have of staying in a curved path rather than accidentally continuing to go straight off the edge of the curve, right, and straight, and then you crash into something because you're not on the road anymore. All right? Anyway, we'll stop there. That's enough. Thanks for watching, and we'll see you next time.